Okay, so let's start. Welcome, everyone. I see most of the folks are here. So what we'll do is continue where we left off from last time and explore a little bit more about CNNs, transfer learning, and so on. But first, let me make a few logistical announcements. The first thing is some minor updates on the syllabus page. So let me share my screen. Yeah, so what I did is on the syllabus page, I separated the focus of slides in a separate section called topic modules, and I have also separated the dates. Okay, so basically we are here to 10, and so from here you can see that assignment 2 is due in a couple of weeks. It's about CNNs that we'll finish up today, and it's also about a simple model which underlies a simple collaborative filtering based recommendation system idea. Okay. Um, the next, I guess, important announcement that's actually from here, you can see that after assignment is due within a week, about a week, you also have to submit an initial project proposal. Uh, and it's an intermediate report, and some details are available on the project page. We can navigate there actually. So you can see the project page has a bunch of details. And what we'll do in that week is basically I'll send out individual emails to each team, and we'll have meetings with each team between me and maybe including Teng and your team separately during the same hours. Okay, instead of a lecture, we'll have one-on-one meetings. So um, so just to give you a kind of a little bit of a teaser, assignment 2 is due certainly, and we'll look at transfer learning today, and that's going to be the content for the submission. And it's anyway in 2 weeks, so you do have sufficient time to internalize what we'll see today to get through this assignment. Um, Finally, one more thing about projects is that Uh, so there are some links here on the project page. Certainly, these are a little bit more about some research, applied research venues, which look at models, including deep learning models. In addition to these, there is a couple of more links that I wanted to quickly share with you. The first one, I think I shared with some folks right after the session last time was this link called Papers with Code. So here you can search for any topic that you are interested in, for example, healthcare, text processing, Twitter analysis, any of those things. And you'll generally see an intersection of deep learning techniques and that domain. It could be even finance, or it could be industrial data, it could be environment data, it could be very different, many different things. And you'll find uh, you typically find papers, and if they have provided code base to go along with it, then you can use that as a starting to think about some ideas. Okay. Let me share it in the chat. And the second link is just a one-off link that I came across recently. It's about section of deep learning and arts. So this is the link, and it's basically a bunch of lectures and from professionals who work in this area. So this is I guess the topic of this course is called Deep Learning for Arts, Aesthetics, and Creativity, and you can see a bunch of researchers as well as working professionals, and they talk about how they're using deep learning or machine learning to enhance their creative activities that they're doing. Okay, so it's also maybe hopefully will inspire you to think of an interesting project if you know for your project. So let me share that as well in the chat. As just one example, okay, and so the more useful resource probably would be papers with code, and you can look at recommendation systems, for example, or any class of models, generating faces using GANs. So many of the topics that we'll see in our syllabus. So you can see that this is a list of topics. It includes something called GANs, which can be used to generate new faces and so on. So, and also NLP related topics that we'll see later. You can actually Google, I mean, not just Google them, but also, use them as keywords on this website to get a sense of what type of problems people are solving here. Okay. Uh, so any questions about assignment and project and how it's going to be for the next 3 weeks? So assignment 2 is due in 2 weeks, and assignment 3, sorry, project and intermediate report is due in 3 weeks. Okay. Um, and I hope by this time everybody has gotten um, comfortable with Python and Collab. If not, I strongly suggest going through the Collab tutorial or a Python tutorial that's linked on the Python links that are linked on the main course page. Or certainly, you can seek a one-on-one with the TA or myself, and we'll try to get you over some initial hurdles. Okay. Um, yeah, and again, as I mentioned last time, annotated slides are available. Annotated slides are available through a OneNote notebook, and it's linked on the course page as well. So it's right here, so annotated slides link. And finally, yeah, and finally about communication, we have a Slack channel, and we do have a Blackboard forum as well. So if you want to use them, certainly feel free to do so. Right now, they're not very active, but you can certainly reach out directly by email because the class size is small. Okay. So any questions about these logistics before I go back to what we want to get accomplished today and so on? Okay, it looks like if there are questions, just put it on the chat. Okay, so if you want to do it asynchronously. So let me get back to where we were last time. So last time we had just had a look at the convolutional neural network architecture, and then we just started looking into how to um, in a sense, debug the CNN in the sense that we were trying to look at what are the different ways to see once you have a trained convolutional neural network, how would you get a sense of whether it's learning something meaningful or not. A few things that we saw last time were, for example, looking at the activations themselves on the training data, or looking at the weight values themselves. Okay, and the last thing that we saw was basically an embedding idea. Okay, and let me actually go back to the slide. Yeah. So let me look at this slide, and I'll switch over to the annotations in a second. So basically, as you know, deep neural networks are basically have this layered point of view, and and they generally tend to have lots of parameters because each neuron in a fully connected layer, for example, will have a huge set of parameters by itself, depending on the input tensor size. And so the number of parameters becomes unmanageable generally. And one of the instances that we were looking at last time was a convolutional neural network. And there are a few, I would say, a little bit informal debugging things, debugging steps that you can do once you have already trained such a network. Okay, or if you download a pre-trained network, you can also look at take some of these steps. Okay, the first step is just look at activations. When I say look at activations, you can think of histograms of activations, histograms of activations, or other statistics. This can be done even while training, for example. And so what do I mean by look at activations, right? So remember, every time you do a gradient update to your parameters, like say W0 B0 to W1 B1 or something like that, you would have computed layer-wise output tensors, right? So output tensors. So the output tensor for like a fully connected layer, which tends to be towards the closer to when you make the class decision, for example, in classification setting, those output tensors, they're not really tensors because they look like basically vectors. So those vectors, you call them activations, and we can plot them. So certainly, you can't really plot vectors themselves, but you can look at like their norms as in its magnitudes, and so on. Okay, So magnitude of a vector is just the sum of the squares of the individual entries, for example, the 2 norm, for example. So that's what we mean here by looking at activations. Similarly, looking at weights is, again, you have a trained network. You can if you can certainly extract out the parameters at each layer, right? If it's a COM layer, you will have a few filters, and each filter will be basically a tensor of certain size, and you can look at the numbers, right? So maybe the numbers are low or high, or maybe they resemble some existing filters that you know from image processing. So those are some evidences of, hey, maybe the network did learn something good. Okay. And with activations, for example, you will know if certain neurons are basically dead, okay, which just means that the ReLUs, because the neuron's output is basically, is some sort of a linear transformation followed by a nonlinearity, right? Like a ReLU nonlinearity typically. And so you will see that the ReLUs are dead in the sense that, if you have 1,000 training examples, if you pass each of the 1,000 training examples through your network and look at the let's say a particular neuron's output, if the neuron's output is always 0, that means that ReLU is really not active. It's never going to output anything. It didn't output anything positive for those training examples. Okay. So that's a bad situation, because in that case, that neuron really did not do any gradient gradient update, because any path through that is the local gradient is 0. So there was no change in the weights. There's no change in the weights affected by that. Which are affected by that neuron. And the last idea, where towards the end of last section that we looked at, is you have the trained network. You can pass through all the training data, which means the training images. Okay. Again, collect the activations at typically the penultimate layer. Okay. And let me actually get to that slide. So let's say the final, let's say you're doing 10 class classification for CIFAR, CIFAR 10, or maybe even MNIST. Then you have 10 classes. Scores would be a 10-dimensional vector. The activations are just the vectors before you do the linear transformation. Okay, so these are the nonlinear transformed pre-activations. So pre-activations are called H, and activations are just called, the transformed versions of pre-activations are called activations. Okay, and they're just think of them as just outputs of each layer, not each layer. So in this case, we're just looking at the output of the last layer. Okay, so you can get this activation vector for every training example. So every training image. Okay, and now you forget about the images. You have one vector per image, or one vector for training example. You can just project them into 2 dimensions using PCA or other methods. And then in 2 dimensions, you get a sense of, hey, if it's 2 images are of the same class, hopefully their vectors are in the same class, or the vectors are similar to each other, because at the end of the day, there's only a simple linear transformation happening. So if 2 vectors are very close to each other, if they just do linear transformation, they kind of are going to be close to each other. Okay. So if you see that if 2 images have similar activation vectors, then that's good. The model figured out the right representations, or the right activations, or the right embeddings of these for this data. Okay, and here was an example where we had a snapshot of for this for ImageNet, some subset of the ImageNet data set, and we had this activation vector was 4096 dimensional for this for an example CNN called AlexNet. And given these 4096 dimensional vectors for each of the training example, we projected it down to 2 dimensions using a technique called TSNE. And we were just visualizing, once you're 2-dimensional points, you can just replace the points with the images themselves and arrange them nicely in a collage. And you'll see that maybe similar images are close to each other. Okay. So this step is also there in our, let's see, if I do this. Just want to, anyway, so what I wanted to do was show you that we have an example. So in the repository that we have, right? So this is a repository, and we have a bunch of assignments and project details and so on. So in the examples, let's look at the example which just looks at this projection operation, because it's really, for us, it's going to be a black box. We really don't need to. We're not going to spend time on trying to figure out how that projection works. but the small code base script shows you what's happening. At the end of the day, for example, you can see in this notebook that we're fetching some data. In fact, it's MNIST data that we're fetching here. Okay? And there's a nice simple function called fetch from openml.org, which lets you fetch different types of data sets, lots of different types of classes, supervised learning data sets. And so we're fetching MNIST. And then we're just picking, so MNIST is this, as you know from the pictures here at the bottom, MNIST is just a black and white image of digits. Okay, and so they are 28 cross 28 pixels in size, and there's no depth. Okay, because they're black and white. And then you can vectorize them, and you'll get a 784 dimensional vector because that's 28 times 28. Okay, so for each vector, that's a feature, and you have a label, which is what digit it is, right? So you can pick those. So in this part of the code base, we're just picking a few of them. Okay, we're picking 1,000 such images from the data set. Okay, so the data set actually has a lot of images, um, probably 6,000 per class or something like that. Okay, so anyway, so we picked 1,000 images. So this is the subsampling. This is indexing, NumPy indexing. And here we're just showing a couple of such figures. Okay, so we actually can use IMShow to show figures. And so we are picking the 11th example. We are reshaping it so that it comes back again from a 784 dimensional vector to 28 cross 28. And then we're just doing a show, and we're just labeling it. Okay, and you can see it's 3,8. Now, the important thing is how to do this projection, right? So now you have these images. They don't really, we haven't embedded them because we just have a 784 dimensional vector corresponding to the image, which is literally the pixel values. Okay, but if we had trained a neural network or some other model, especially for CNNs, you would get these activation vectors. Instead of just vectorizing the image itself, you can vectorize, you get a vector which is the activation vector, right? So just to ground what I'm talking about, let me go back to that uh, animation that we saw last time. Um, to the convolutional network. Yeah. So let's say I draw 3 here. So all I'm talking about is that, if you have a model, so you can certainly vectorize this image 3 itself, right? You can just say, hey, take first row, then concatenate with the second row, concatenate with the third row, you'll get a really long vector. Okay, that's at the bottom level. Instead of that, you can, what we're saying is take the penultimate tensor. Okay, so instead of the score vector, which is 10 dimensional, you can take the penultimate tensor, which could be whatever. In AlexNet, it's 4,096 dimensions. Okay, so this vector, if you now project down into 2 dimensions, you would get something nice. Okay, here in this example, we are not doing that. We're just we are projecting down the original image itself, original vectorized version of the image itself. And to do that, it's very, it's just 4 lines of code. Okay, so from sklearn, for example, sklearn makes it easy. So you import tsne, and that's it. So this extra stuff is just for extra, cleaning up parts. But basically, you can say, hey, how many dimensions do you want? 2 dimensions, and you can just say instantiate an object called, from the tsne class, and then fit transform of the input data. That's all we need, and you'll get a result object, and you can just look at the shape. It's basically just going to be in this case, it's just going to be 1,000 rows times 2 dimensions. 1,000 rows because there are only 1,000 examples in this subsample data, and that's it. It's a 2-dimensional. It's a matrix. Okay, and you can plot that matrix, and you can see the matrix here. We have not optimized anything. There's no learning here, so you can see how like 0. If you just look at the vectorized versions of 0 and project them into 2 dimensions, the blue, the light blue area is towards the left, right? And similarly, you can see the green correspond to 6 are in the center top, and so on. Okay, so it's already, you can see that the classes are somewhat separated, but if you had really taken the activations, you would see that they are separate. Okay. Any questions here?
So can this package be used with multiple different kinds of data, not just images or not just also just data points?
Yeah, exactly. That's a great question. You should. So actually, this is one of the things that you should do while doing EDA for any ML technique. Now, forget about deep learning or images. You should. It's basically very similar to PCA. If you had data and you, let's say you had too many feature vectors or some too many features, you would want to do PCA, right? To some maybe dimensionality, reduce dimensionality, and so on. But that's one thing. But you can. That's for dimensional reduction. Here, it's just visualization of your, for example, data itself, right? That you can do. Certainly, you can just project your data down, feature vectors down into 2 dimensions, and see if the feature vectors are somewhat separable in this 2 dimensional visualization space, right? Yeah, you can do that for anything else. Like if you had columns like age, income, and something else and something else, a typical financial data, for example, or other numerical data, you can certainly do this. Yeah. And in fact, there is a couple of links here to just which really, and which really spend some time on not just TSNE is just one nice example. I think these guys do it on MNIST. So on sklearn's website, you can see that they have done it for lots and lots of data. So if you just randomly project data, it doesn't have to be images, as you said. You can, if you randomly project data, something happens. If you do PCA, something happens where 2s and 3s and 8s and 4s are somewhat far away from each other, but you'll see that there are tons of projection methods. Okay. By the end of the day, let's look at TSNE. So you can say TSNE, once you optimize the model, it's, like MNIST is happens to be an easy enough classification instance, a classification data instance that many classifiers pretty much go up to, have achieved very high accuracies, which means that they can really get these activation vectors, for example, to be quite uh, far away from each other. So you can see the classes are nicely separated, clustered. Right? So yeah, have a look at this. And uh, yeah, I think I had one more similar image, which I can maybe share here on the chat. Sorry, this link, I just got it from the example itself. Okay, so in the example at the top, it shows, I didn't write this code. This is written by on somebody's blog. And certainly, if you just look at scikit-learn's TSNE, the function documentation, it'll just show you that those are the 4 lines required. These are the 3-4 lines required to call TSNE and just fit dot transform. And that's what I guess is the beauty of scikit-learn, to be able to do these steps, in a very easy way, in a very unified way across multiple techniques. The last, I guess, before we jump onto a few more things about debugging trained models, the last one is just visualizing MNIST. MNIST, I think some of you might have worked on. For example, when I teach 575, I do use MNIST data, but folks have, might have seen it in 572. So here's yet another visualization, same idea. So if you look at, yeah, TSNE, sorry, not this one. So yeah, so this is an image of TSNE actually training in, it's an animation for TSNE learning to uh, embed the embed the data set. So if I play this, um, you can actually see which cluster belongs to what, and they have made a nice animation where you can point to a point and you can get the image for that. But this is exactly, all I'm saying is the function calls are simple. You ultimately get a 2-dimensional matrix of, for every image, what's the 2-dimensional point related to it, or a vector related to it. Once you know that, in our slides, we just, we had the 2D points. Instead of the points, we just plugged in the images here, and that's why it looks like collage here, but it's all the same idea. Okay. So Um, so okay, now what we'll do is jump on to the next couple of techniques in terms of like kind of visualizing or diagnosing these CNNs. But before that, I wanted to quickly close a few things. So let's close this. Projects close. So let me lay out, and since we just caught up with what we saw last time, I just added the TSNE example as a way to show you that it's not complicated as long as you consider it as a black box. Certainly, there's some details of how TSNE achieves this embedding, and what is what does TSNE even mean, the name itself, and so on. There's some details, but I think for now we will not worry about that, because just think of it as replaceable with, let's say, PCA. It's just PCA is linear dimensional reduction technique. TSNE is doing something non-linear. Okay? But at the end of the day, it's reducing dimensions. Okay. So we were talking about the second point last time, actually, which is how to debug or get a sense of do some diagnostics on a deep neural network. And what we'll continue from there is we'll look at how to transfer parameters. Okay, and this is going to be a key idea, and it's also going to be related to you assignment 2. It's called transfer learning, and we'll see some details on how to do that. And it's also quite intuitive and straightforward. Then we'll try to look at a couple of examples of some extra, I guess, they're not layers. They're not, they're part of some model enhancements. Okay, and one of them is a regularization technique called dropout. And the second one is some sort of a transformation that happens between layers to help. It seems to help empirically in terms of training of training of a neural network in general, including a convolutional neural network. Okay, and we'll look at those two tricks. And also look at something called data augmentation, which is quite popular for image data. And then hopefully we'll get started with text. Yeah, hopefully we'll get started with text and look at some basics of NLP and so on today, hopefully. Actually, that reminds me, this page is not super updated yet. So update is just in terms of ordering things. If you look at the syllabus page, oops. I have moved up one of the topics from which was towards the end, which is actually advanced NLP. So what changed is from, I guess, last week to this week is I just moved up a lecture. It's not yet, we're not yet there, but it's about NLP and it's about some newer models for dealing with text data. It's better to group it with when we are seeing text, and text and some other related models. And then towards the end you'll not have one specific lecture on text again. So I just moved the text lecture uh, to closer to when we're touching text. Actually, hopefully we'll start looking at text related models today onwards and next week. Okay. So what was this? Yeah. Okay, I'm going to switch to the notepad. Any other questions in the meantime of where we're going? Okay.
Nope.
Yeah, thanks. So what we'll do now is continue with one more, what I feel it's a very interesting technique, which is visualizing whether the model works, in this case, a CNN, by introducing occlusion. Okay, occlusion just means introducing something in between, right? Occlusion means occluding things is just covering up so that you don't see the image, for example. Um, so, so the key idea here is to say, hey, I have the trained CNN. Now I want to know which part of the image is actually leading to a certain classification. Okay, so for example, there could be some parts of the image that are getting picked up to say the class is A or B. For example, let's say you're classifying cats versus dogs, and it happens that most of the figures, most of the images of dogs are in the are in the open, so you actually see a lot of greenery, and so maybe the classifier is picking up the green patches, okay, around the dog to say that this is a dog instead of dog specific features, right? So you may get, you'll probably you will be able to debug some things like this using this technique. So what is the key idea? The idea is to Okay. 1 second. Right. Yep. Yeah. Sorry about that. So the key idea here is to create a plot, a two-dimensional plot. And what we're going to plot is the probability of a class of interest. Okay, so let's say we want to say what is the probability of dog, okay, for the input image. Now, this is one number, and so there's an input image of a dog. Okay. What we'll do is we're going to introduce occlusion, which just means that we're going to cover up parts of the image. So okay, let's say we break the image into 9 parts. So what we'll do is we'll cover this part up and then say, hey, what's the probability of dog? Okay, it'll say, hey, this is still 0.9 because the dog is actually in the center. And next we'll cover up the second patch and say, what's the probability of dog? Maybe it's still 0.9. Okay, and maybe it's dog is in the center. And so hopefully, if the classifier is working well, if I cover up the area where the dog itself is, maybe it says the probability of dog is 0.01. Okay, hopefully it decreases. Okay, now you collect these numbers, okay, these probabilities of dog or not dog. So you'll get 0.9, 0.9, numbers, maybe 0.01, some numbers, and so on. Okay, so this is a 2D. I mean, this is what I'm calling as a plot of the probabilities. Okay, so class of interest is dog in this case, and I'm just saying, hey, here's the image, and this will show that, hey, somewhere if you occlude or cover up the image, then you're losing the signal for it to be a dog, of it to be an image of a dog. Okay. So here are the actual examples. So occlusion is in gray. So you can see the occlusion here, right? Or here, or here. Okay. These are the occlusions. And that's just one example. But what you can see at the bottom is actually that instead of that 3x3 thing where I said we're going to insert probabilities, here they've computed these numbers for a really, so they're moving this occlusion, let's say, like, for example, from here to a little bit to the left, to a little bit to the, sorry, a little bit to the right, and so on. They are just doing basically the same idea of sliding occlusion from left to right and figuring out these numbers. And you can see that, for example, let's focus on the leftmost bottom finger. Okay, so here you can see that red means high and blue means low. High probability, sorry, and blue means low probability. You can see that if the occlusion comes to the center, okay, in this area, actually I'm using a red color here, maybe some other color. Come to the center, if you occlude over there, you can see that the probability of, in this case, Pomeranian is going all the way to 0, because as I said, red is high probability and let's say blue is low probability. Okay. So here you can at least see that, hey, if I cover up the actual dog in there, the probability of dog is actually going down. Okay. Same thing with I think predicting car wheel. The car wheel is the label of interest, and if we are seeing, hey, if I occlude other parts of the car, it's not really affecting whether we are, what we're saying as the uh, label to be car wheel. In fact, it is actually, I would say it is, in the sense that if you see this region, if I occlude, it's saying that the probability of car wheel is actually low. It's not super low, but it is low, including also this region. Okay, so these are, I would say, somewhat spurious signals. What the classifier should be doing is, if I really cover off the wheel itself, then certainly you should say, hey, there's no car wheel here, right? So these are some things that you can do. Of course, these are somewhat limited in scaling, right? You can't really do it for all images because somebody human in the loop, so humans have to explicitly look at it and maybe make sense of these diagnostics, but it's certainly helpful. Okay. So is the idea clear? Any questions? Okay, if there are no questions, then the last idea is about, it's centered about, so you have this, again, a trained network. And what you're trying to do now is to say, hey, the weights are fixed. Now, can I try to figure out what is the input x? So I have something like f weight, right? So w comma b of some x, and it's producing scores, right? It's not just w comma b. It's it's going to be a lot of parameters depending on how many layers you have and what architectures what layers you chose and all that. But let's say w comma b is already fixed, right? So what I'm saying is, can we? So we know, so let's say scores are 10-dimensional, 10 cross 1. Okay, it's a 10-class classification problem. And the idea here is that, hey, can we figure out what is the x which maximizes one of the score coordinates? Okay, so w comma b is fixed. Now we are asking, find x that maximizes, let's say, score 3, okay, or score 10, or score 1. If it is MNIST, so if it is MNIST, actually, let me, if it's MNIST, let me index it by 0, 3, and let's say 9. So that we know that the index is actually the label. If it's MNIST, so score 0 to be the highest, hopefully the ideal input image should actually have a 0 there, right? So that's what we want to find. And this finding x, which maximizes a score, again can be done using gradient descent. Okay, so why is that? That's because you can have this optimization problem, maximize score 3, which is let's say f3, right? The third coordinate basically of with the w comma b of x over x, maximize over x. Okay, so this, now you start with x naught, do a gradient update to get x1, gradient update to do x2, and so on. So just flipping what quantities you are doing a gradient update over. Okay, so previously while learning, while training, we cared about gradient updates on the parameters. Okay, data is fixed. Okay, we are not changing anything about data. Certainly we may have to batch the data and all that. That's a different consideration. Here, the parameters themselves are fixed, but what we're trying to learn is the best input. Okay, best input for a certain class. Certainly, I mean, so if you do this naively, it actually does not work, unfortunately. So what folks have done is start with some good initial images. Okay, so good initial images, and these are, I mean, that's what they're calling as natural image priors. So basically start with some initially good images. Okay, for example, you could start even with the image 0 itself. Let's say you're trying to maximize the score 0. Start with image 0 itself, and you'll see that eventually the best image that gives you the highest value for that coordinate, score 0, is going to be the image 0 itself. And in this in this example here in this slide, so if you do that gradient optimization, you can see that for the gorilla class, there's some patterns. I mean, you can't really see the patterns really well, but you try to see what's the best image. Okay, so cliff dwelling, I don't think it's a good example, but here you can see some more examples, right? So for example, you start with an image prior, and you want to figure out, hey, can you, so ImageNet has classes, 1,000 classes. So one of the classes is goose. And so you want to figure out, hey, to maximize this goose score coordinate, what's the best image I can give you? The best image input is this. Okay, it's not going to look like a natural image, okay, natural photograph of a goose, but you can see that, hey, as long as a goose is here or here or here or here or here, or if this is the image, this would be the one image which would get you the best, highest score for the goose coordinate, and then maybe not high scores for the other ones. Okay. And similarly for ostrich, this is the best image. Okay. So this basically, we're finding images that activate a neuron. In this case, the last, so activate any neuron, actually, we can do that. It's the same optimization. But the last score, when I say score of goose, that's actually a neuron, right? Remember, every output tensor, every cell value is a output from a neuron. So you can pick the last one, or you can pick anyone from any intermediate layer as well. Okay. So that's an idea here, and that was explored a few years ago. And you can check out this link below for a video demo of this idea. I'll try not to spend too much time here because there are all sorts of patterns.
Professor,
yeah.
I had a question about this. I guess a couple ones. First question. So you say you're trying to maximize the score. Are you trying to maximize the raw score output? Or are you trying to maximize this score versus the other potential neuron outputs? So you're trying to like maximize the difference between, goose versus ostrich, or are you just trying to maximize goose?
Yeah. That's a great question. I haven't told you that level of detail. So it's this a design choice. So
Okay.
you can certainly choose, let me just maximize, focus on one coordinate and forget about, I don't care about what scores are being output on the other coordinates. Or you can say, hey, this score should be maximized. And then you can do you can do some sort of minimization, which basically just is minus some sort of let's say gamma times F4, let's say the fourth coordinate, fourth score. I want to, sorry, gamma just is like a scaling number. Of the input minus, let's say, gamma times F5 of the input. So you want to say, hey, I want third coordinate to be as high as possible and all the other coordinates to be as low as possible to get me the best image. So you can do that. Yeah, certainly. Great question.
And then I had a second question. I know I've seen other like research and stuff where it talks about they have an image of a gorilla or whatever, and they show by changing a couple pixels that classifications misclassify things as like an ostrich. Is this how they do that technique?
So this is just about, that's a great question. Yeah, somebody had something to add? I heard some voice. Okay, so that's a great question, John. Here we're just saying we have a trained network. Get me the, I'm being optimistic in this step, in the sense that, hey, I have the trained model. Tell me what's the best image I can show to get the right class. In this case, let's say ostrich or gorilla or whatever. So that other side of, so this is like being optimistic. Now you can go take a pessimist hat and say, hey, I know that, for gorilla images, I know that this gorilla coordinate, let's say, coordinate number 4 or 5, whatever, 4, let's say, has to have the highest score among all the, 1,000 coordinates, let's say, it's an ImageNet situation. But what is the minimal change should I introduce an input such that it flips its class? So that's I guess a pessimistic hat question. In fact, it has spawned so much research, about, I would say, 10,000 papers by this point from past 5 years of research, and they all are looking at, hey, how do I attack pre-trained models? Okay, and not just deep learning models. You can do that for financial models, which which say this person should get a loan, this person should not get a loan, or other things, face detection. So basically, or even like for self-driving cars, they need to detect road signs and then say, hey, in the stop sign, the image looks like a stop sign for us, but what is the minimal perturbation that we introduce to that image so that the car thinks it's not stop sign, actually, go faster or something. Okay, so that's called adversarial machine learning. Adversarial, I guess the word just says that, hey, how do I pawn a model like a computer system? So that's actually, those problems also look very similar to this. So this type of optimization problem, that's very similar.
Okay.
It turns out,
it
turns out it's just to gradient descent. Gradient descent, those such things.
Okay, thanks.
But it's good to know because, as I said, it could be an interesting project. I think some team before, one of the previous semesters tried doing adversarial ML for a specific class of specific type of data set. Yeah, I don't want to spend too much time here. You can pick any neuron, as I said. It doesn't have to be the score coordinate at the end, because, as I said, any tensor level, any layer, you can pick any layer, output tensor corresponds to a neuron, and you can always pick any neuron anywhere and say, what's the input pattern which maximizes that neuron's output? Okay. So, for example, if you're very close to at the bottom, you'll have simple patterns, and if you're very close to the output, you'll have more complicated patterns generally. Okay, you can try this, or you can at least look at the video demo by these folks who did this. And very similar idea is the following, where you don't say, hey, I don't want to find a freeform image which maximizes the score of, let's say, a goose or an ostrich or something. Just tell me which images in my training data are the ones which are triggering the score for, let's say, the goose coordinate the highest, or the ostrich coordinate the highest. So that was like a little bit of a restricted search. I mean, it's not really a free-form search. You're just basically picking every image in your training data and figuring out, hey, which images are the ones which are firing, which are producing the highest score, for example. So that's like saying, hey, what's the most positive examples, what's the most negative examples? But you can also do this for neurons which are not at the score level, right? So if you go back to that previous idea, all I'm saying is you can pick any layer, maybe the 5th layer instead of the 10th layer. 10th layer, let's say, the scores, producing the 10-dimensional score vector. Maybe the 5th layer has some neuron, and you want to say, hey, which of my training data points are triggering, making this neuron output the highest value. You can do a linear pass over training data, pass it through your network, and therefore pass it through the neuron, keep remembering what the neuron's output was, and just sort the outputs to get a sense of which neuron is sensitive to which type of pattern. Okay, so I think this is just an example of a given neuron, let's say at the fifth, I guess, pooling layer or before it, just seeing which neurons, like what is the triggering value of the neuron for, and what is it seeing, and what is the image. Okay. So it's a very similar idea. It's just trying to say, hey, in the training images, which images are triggering which neurons the most. And you'll see that the idea that what you want to get from here is that, hey, if some neuron maybe at the fifth layer or maybe closer to the output, that neuron hopefully is triggered by similar type of images and not triggered by other types of images. For example, always the face of a person, or always the a dog, or always a house or something. So that's the idea here. And all these are, by the way, somewhat informal diagnostics, very different from some of the diagnostics that you've seen for linear models and so on. But folks do this, and there are many others. We just saw examples here. Any other questions before we talk about an important straightforward idea, which is called transfer learning? Okay, if not, let's look at this topic. See if I had additional points to make. Yeah. So this is basically assignment 2, one of the questions in there. So let's look at transfer learning. So what is transfer learning? So the key idea is that very few people train such a deep neural network, deep feedforward network, or a convolutional neural network from scratch. And that's because I think some of you have already hinted it when you asked several questions in the previous sessions. Hey, how do I choose how many? And in fact, you also checked it out in the assignment 1. How do I know how many layers? How do I know which layer follows which layer? Should I use fully connect layers at the beginning, at the end? Right? How many filters to use in each con layer, for example, or including how many hidden units to use, which nonlinearity to use. Should I use the same nonlinearity throughout the network, or keep changing nonlinearities between layers, right? Or even at the level of individual neurons, right? So there's so many choices, and so training and figuring out, navigating all these choices and figuring out the best, I guess, architecture for your applied problem becomes challenging, and some folks have the energy and the budget to do that, okay, to figure out the best architecture and all that. And that's again very similar to adversarial machine learning. It's an area by itself. It's called neural architecture search. But here, what happens is in many business problems, the data set that you have is much smaller than the data set that researchers in big labs have already trained on, or in academia have already trained on. Okay, for example, ImageNet had about just the classification task. ImageNet itself had 14 million examples. In the classification task, about, I think, 1/10 of that, about 1.5 million, 1.4 million images were used, okay, for a 1,000 class classification problem. Now, if you pick any applied problem, I don't think, or at least it's unclear if folks will have, I think the median data set size will not generally have that, will not have so many images and so many labels. First of all, labeling images itself as a annotation is a task that we will not cover in this course, but it's a big data pre-processing step, especially in an applied problem. You may have to spend some time annotating images. So folks may not have that big of a data set. So in that sense, there's a very nice way to have limited data, as in have small data, okay, where you will say, hey, the deep neural network that you're going to use has much more number of parameters, or is too complex for the data set that I have. That's still okay. What we'll actually leverage is called transfer learning, where you try to leverage a pre-trained model that you can download from the internet, okay, and given by some big tech companies or academic researchers or whatnot. And you start with that network, that pre-trained network or pre-trained weights that are already set to some nice values because they did, let's say, train on ImageNet or whatever. Then slightly adapt them so that the network performs decently on your problem. Okay, of course, there are some assumptions built in here, and we'll look at that. There are two types of of transfer learning. One is called a simple one. It's called feature extraction. And second one is a little bit more involved than feature extraction. It's called fine tune. These are just two popular ways of doing transfer learning. Okay. And the idea is, as I said, very straightforward. You get a pre-trained network. And let's talk about CNNs because we've been talking about CNNs since last session. So VGG and AlexNet were, I would say, the older generation of CNNs. This is from 2012. This is from 2014. There are newer ones like ResNet. I think this is what you'll use in your assignment. This may be 2016, I guess. I don't remember. So get a pre-trained CNN, and what you generally do in the feature extraction way of doing transfer learning is that you just get the activations. Okay, so you remove the last fully connected layer, the one that produces the score. If it's ImageNet, then the score vector has to be 1000 dimensional because it's a 1000 class classification problem. So you just drop that. So you just drop this, and here you have the activations. Okay, this is the same thing that we saw when we were talking about projecting down to 2 dimensions. Okay, so you get activations, one activation vector for each of your training examples. That's what you would have done in the diagnostics part. Here, we just drop the last transformation, the W and B, which leads to score vectors. Let's drop it and retain all these weights, right? All the weights involving, let's say, in the con layer, here, not pool, maybe in fully connected layer and so on, and use them to get embeddings of my data set. Okay, so I have a separate data set. I got this model. I'll drop the last layer. Okay, and it's very easy to do in Keras as well as PyTorch, and you'll maybe explore it. You'll explore it in actually in assignment too. And in feature extraction mode, you'll just get embeddings of your data sets images. Okay, once you get the embeddings, now it's not really an image-specific problem. You have embeddings, you have labels. You just have to you just have to learn a model which goes from embeddings or the activations to the labels. Okay, and that you can just do by even just applying SVM, for example, okay? Because the hope is that the embeddings or the activations here are really good in the sense that similar classes of images have similar embeddings. Okay, so that's already taken care of. So you can have a very simple model once you get the embeddings or activations. Okay. So, and that's explicitly stated here. And that's what an embedding means. Just think of it as the activation vector right before the score vectors is computed. And it's just a representation of the image. Yeah. And we suggested yeah, as I was saying earlier, you can use the activations or the embeddings to input, use that embeddings, I guess, activation for my labels. So whatever I is equal to 1 to, let's say, 1000 of them. So you have this, you can just train a linear model like an SVM. I mean, if it's if it's a binary class classification problem, or you can use the multi-class logic regression model that you've seen already in the first session, right? So you can use any model here. It's not also necessary that you have to pick the last, last. We can only chop off the last fully connected layer. Okay, we can actually chop off more. We can, for example, sorry, let me stay here. We can chop off more. For example, we can even chop off up to here and say, hey, these are the vectors, or these are the tensors that I should be using as the embeddings of the image. Okay, that's fine. When would you choose to chop off like a little bit early in that in that neural network? Is when your images are very different from, let's say, the ImageNet images. Okay, let's say you're trying to work with let's say medical data or some security data or something, or drone footage, then it's not the images are not going to be very similar to the ImageNet dataset images. So you may have to try out chopping off a little bit early, and the intuition is that early on, those neurons are trying to fire, or I guess fire just means output high values for generic or smaller features because they're I would say they're what is it called, the spatial field of view. Spatial field of view is small, and so the early on neurons are triggering for somewhat generic features like maybe circles and squares or edges and so on. The neurons later on, they generally trigger for more complex features which are related to the classification task at hand. Okay, so that's one thing that you could do. So is feature extraction idea clear? It's a very straightforward idea. You just have your applied data, pick a pre-trained model which is trained on something else. Hopefully that something else and what data you have is somewhat similar. And then you just get embeddings for your data set and then train a simple linear or nonlinear classifier. You can again train a neural network as well. Okay. So that's first type. So now let's move on to the second type and contrast it to the first one. And the second type is called transfer by fine tuning. Okay. So here, what we do is we still retain, in the previous case, we were just taking the embeddings and forgetting about the network. Okay, so network's purpose, the pre-trained network's purpose was to just generate these vectors, okay, or some feature vectors for each image. And then we would forget the network. Here, we'll retain the network. Okay, so we are actually doing a little bit of an operation on the network. And we're just gonna change the network a little bit based on what our task at hand. Okay, so for example, you can say, hey, maybe the last fully connected layer is 1,000, 1,000 class classifier. It produces 1,000 scores. Maybe you're just doing a dogs versus cat classifier. Then you can just change the last fully connected layer to a layer which only produces 2 scores, right? So that means this last layer is gone, but you still retain, the rest of the network. Okay, so you just adapted the network. So this, if the weight here was W comma B, the same weights here are going to be W comma B. Let's say for the filters here, the same weights are going to be there. And then the fine tuning part says, hey, now let's just do the same idea, gradient descent, where we'll update the weights of, since we introduced a new fully connected layer, certainly the weights are not the best choice. So we need to go from W0, B0 to W1, B1, and so on. But we'll also update the weights of, maybe the other layers. Okay, and sorry, not that one. This one, and so on. So we'll update the weights, but we'll only update it, very little. Okay, so which just means that the learning rate, remember the weight update rule had that previous value minus some learning rate times the gradient, right? So the learning rate will choose quite low. Okay, for example, you can choose a learning rate to be 10 to the power minus 5 or something here. And maybe for this guy, you choose a learning rate to be 10 to the power minus 2 or 10 to the power minus 1. So that's called fine tuning, where you may have to even fine tune all the way to the first layer if you want to slightly change the weights. So basically the idea is, hey, the new network has been already the initial weights for many of the layers are pretty good. Of course, the last layer, since it's a slightly different classification problem, we anyway have to learn the weights. And let's slightly change the weights of the previous layers, okay, in comparison to the last bunch of weights, which have to be changed quite a bit. So that's the idea of fine tuning. Yeah. Any questions about up to this point?
I had a quick question. Let's say you want to do like an ImageNet analysis and you're trying to fine tune your model. But let's say your images are very different than like the original model. Let's say the original model was, I don't know, just normal ImageNet, but you're trying to do a dog cat classifier on really low resolution images.
Yeah.
At any point, does it make sense to change up the pooling layers? Like, let's say, oh, my images are much lower res. Let me just throw out a couple pooling layers. Can you do that, or does that not work in practice?
That's a good question, John. So I think if you change these, then you're really in uncharted territory, because they are supposed to be there for, at least for the original case, we know what the purpose was. I think if you drop them, that's fine, but you will still, if you do fine tuning after dropping them, that's okay. That's something you can try, but it's unclear what their effect is going to be, and they may actually
It might get you bad results.
Yeah, decrease the effect that you're hopefully going to get from transferring prior training. Right.
Okay.
Yeah.
Thanks.
Pooling, maybe not, but the thing is, there's also this other issue that you brought up, which is, hey, so for most CNNs, by the way, when you train CNNs, they take fixed size images. Okay. Now, if you have a slightly different size image, then how do you pass, like at test time, let's say you trained images on, okay, at training time, at least you can control the size of the images. Maybe all the images are the same size and you pass it through and you learn the model. Now, you deployed it somewhere. And now people, if they take photographs from their iPhones or, other things, they'll have different size images. And there are, very simple fixes where at the data pre-processing step, you rescale the image. Okay. Now, if you already have a low resolution image, it's unclear what you can do. Maybe you can replicate the image so that it becomes bigger and the same size and so on and so on. But yeah, there are some data pre-processing steps that one needs to be concerned with here. Okay, and you'll see that later on when we talk about data augmentation. It's a good question.
Thanks.
Yeah, so this slide is just it's a slide from a paper from half a decade ago, and just showing what you do from an image to let's say classification problem. You do a lot of things. Okay, so here there's some names which I don't want to get into, but these are steps that you would do for many different types of image related problems, and they are listed here on the x-axis: object classification, scene classification, flower recognition, and so on. So there are different problems and different types of data sets. So, but they all need some lot of pre-processing, which is in the green at the top. So instead of that, this paper, what they did is say, hey, let's pick a pre-trained model and use that representation, basically show that transfer learning works. And you can see that by just using a pre-trained network, they're able to get really good results. So yeah, CNN off the shelf here, the second columns here. And yeah, so here we are showing what they're showing is the green represents I think a non-neural network or non-CNN based solution, and higher is better. And you can see that the moment you introduce just transfer learning, you're actually doing better than. So remember, the green stuff is, or the benchmark is not really relying on transfer learning. And here you're really saying, hey, something was trained on a really large data set with lots of classes. Let me do now just do some specific classification, then you can actually really improve. Okay. Not always the case. For example, here you can see not improving, but many of the times that's good. And you'll see a very similar idea in the later part of today's session or early next session, which is about using such embeddings or such representations for words. Okay, and so it's again the same idea applies, where somebody else is trained to get these vectors for words from some large data sets, and then for your applied problem, you just pick up those vectors and work with them as if those vectors are are numeric representation of the words. Of course, images, there is not finite number of images. For even a single object, you keep taking images from different locations, you get many different images. But words, you can't really do too much. I mean, for each word, you can, even if you change the application, the word remains the same. So there's slight difference like that. Yeah, and just a quick aside on we've been talking about classification quite a bit. I just wanted to quickly mention a couple of other machine learning tasks or prediction tasks that you can do with images, and you will see that it's not that different. Okay, so for classification, remember we were using logistic laws, are basically the softmax or cross entropy laws. There's another problem called localization. Okay, so here you're not trying to say what object is present in the image, but also figure out the coordinates within which the object is going to be there. Okay, and that's called localization. Object detection is the same idea, where you could have multiple classes or multiple objects in the same image, and you also need to say, hey, where in the image is that thing and what is it? Okay, Okay, so you also need to say which class and where is it. Okay, and segmentation is another slightly different problem where you want to carve out, get the boundary of, let's say, the cat and everything else, or the dog and everything else. Or it makes sense for example, self-driving applications where you get a video feed from the front and you want to say road and not road. You segment the input incoming feed, for example. Okay. So these are some other example tasks. We'll not get into any of them in any detail, but I just wanted to point out, and they're going to be very similar to, it's just going to be a change in the loss function. And of course, if you think of neural networks, CNNs by themselves are very good for classification, as we saw so far. But for, let's say, segmentation, you may have to do a little bit more. Okay, so by the same time, the little bit more is just going to be some sort of a maybe potentially using new layers, or just using the CNN layers in a clever way so they can actually do segmentation, or you can actually do localization detection. So it's just a change in how you layer things in the model, and it is going to be a change in the loss function. For localization is clear, right? You want a bounding box, not too big, not too large. So you need to have training data where somebody else has given a bounding box where in this training data, this is supposed to be the training bounding box. And that's how the model will learn to figure out bounding boxes. Okay. So there's of course that an extra annotation that is needed compared to classification. Yeah, so I guess this again comes back to some general, I guess, rule of thumbs. They may not really hold all the time. So if you have small data and the data set is very similar, then you're in a really good situation. But if it's a really different data, then you are out of luck. And if you have a lot of data, then and the data set is similar, you can just do fine tune a very little, just little amount is fine because you have a similar data set. But if you have a lot of data and if you have a different data set, you can certainly fine tune a lot, or you can actually start from scratch as well because you have large data. Okay. And this is key for projects which will rely on images. Okay, so certainly do transfer learning and you'll get away with not having to burn a lot of computational budget. Here is a quick example of I guess one of the nicest CNNs from early days. It's called the VGG. It came second in the 2014 competition. And this is the one which I guess introduced the smaller filter sizes and used ReLU. And you can see a very nice architecture here, right? It's just image, con layer, max full, con layer, max full, and so on up to some point, and then fully connected, fully connected, fully connected. In fact, the most of the weight, or most of the, I would say, the largeness of the model is because of this fully connected layers. Because if each, there are like 4096 neurons here, and whatever is the input tensor here, if it's like 1,000, even if it's, the input tensor, if you once you vectorize it, if it's 1,000, then each neuron is getting about 1,000, weights related to it. And so 4,000 times 1,000 is already like a 4 million number, right? Right here. And if you have, again, 4,096 times 4,096, again, 16 million numbers there, right? So there's some explosion in the number of weights in this model, and that's predominantly because of the fully connected size, fully connected parts. This part, the size just depends on the number of filters you use, and the number of filters is written here, 64, 128, 256, and so on. There are some choices that they made, and it worked pretty well at that time. And actually, yeah, I want to quickly show you another example of such a diagram. So any questions, by the way, at this point?
Professor, I have a quick question.
Yeah.
So all this transfer learning models, is it just like using like a built-in function or a built-in algorithm, just calling those
Yes.
existing transfer functions? Okay.
Yes. It is. And so let's actually see that a little bit today. So let's come back to your question. So is it a built-in function or not? So I wanted to just spend, since I was showing VGG, I thought, this link, by the way, is it's a link where I found they had plotted different, at least diagrams of different architectures. So AlexNet is from 2012, VGG is from 2014. you can say ResNet is something that I think you will work in your assignment too. And the biggest one, I don't know if this is the biggest one, but for example, this one has 56 layers. Okay, I think ResNet has also 108 version, but the version that you probably can use in your assignments could be 18 layer version or 50 layer version. So anyway, so this is a nice picture where it shows that, hey, there's so much, like you can see that the ones in the center have so much complicated in terms of how the layers are wired. Okay, and you can see AlexNet and in particular VGG. If you click on it, you can see, hey, there's a, for example, con layer, ReLU, pooling, and then flatten. Flatten is just vectorization because at the end of the day, you don't need a tensor, you don't need a cuboid shape if you're connecting to a fully connected layer and so on. And that's, it's just that nice thing that we saw in the slides as well. But you can see that there are some intermediate models that came about in 2015, for example, Inception V3. They have quite a messy network, right? So this is not something that, this is exactly the exploration that, they had the budget to do it and they explored and they got some model here. But if you're an applied data scientist, you really will not have the budget to explore all sorts of architectures. Okay, so that's where I think also transfer learning helps. In addition to, of course, using pre-learned weights from other larger data sets. Let's look at LessNet a little bit, and then let me come back to your question about is it a built-in function or not when we look at an example. So if you look at ResNet, okay, the last column here, so you can see something interesting happening. So which is, you'll see this pattern repeat, it's a 56 layer thing. So there's a lot of layers, by the way. You can see that there's a bunch of operations like con, and there's batch norm, which we'll see in a few minutes. Some, forget, don't worry about the batch norm box here, but there's a con layer, ReLU, con layer, and then there are two arrows here, right? So starting from the same point, some tensor, I'm passing the tensor through one path, which is through con layers and all that. I'm also passing this tensor straight, okay, without doing anything. Okay, and then I'm doing some sort of a plus. Just think of it as a concatenation operation, or just adding the vectors themselves. It could be either, and then again moving forward. So you'll see that this pattern is repeating quite a bit. Okay, so that's why the name residual network comes from, because it's actually doing. You can think of this as residuals, where this as in like the yellow box at the bottom. I hope you can see my mouse. The yellow box at the bottom is passing through some nonlinearities, some transformations, like con layer and all that stuff. But there's also a direct connection to the output, okay, which is this direct vertical line to the left side. Okay, and that's basically a residual connection. Okay, it's basically saying, hey, I have added all these nonlinearities. If they're irrelevant, just pick their weights appropriately such that path has no impact, and so I can directly go straight to the next stage. Okay, next I guess meta stage. So I would suggest have a look at this last ResNet diagram as you work through assignment 2 to get a more feel for what is that black box. Okay. Now coming back to your question, so let's actually look at our notebook. This time I'm, instead of showing it in collab and doing it in real time, I'm just going to try to see if I have the outputs here. I do have the collab version running. Okay, the outputs are there. So in the assignment, you'll have to, I think you'll be using ResNet. And in fact, you will be relying on this notebook. For example, I strongly recommend running this notebook in collab. I could do it in real time, but in the interest of time, I will skip it. Actually, maybe. Sorry, let me do it because I want to show you something quick. Google Drive. No, it doesn't show. Let me just put Drive. Yeah. So there are 2 points. The one point is something I want to introduce, and the second question is about built-in functions. So you can see there's a function, there's a importing of a package here, Torch Vision. Okay, so that's the package on the, at least on the PyTorch ecosystem, that will let you import models, and it'll also let you import data sets, so you can actually get the MNIST or CIFAR10 and all that stuff directly, by just using these functions. So from models, you can import the appropriate model. So let me see what model. Sorry, let's skip all this code for a second. Yeah, so you can see models.resnet 18 and pre-trained is equal to true. That actually gives you a model. Okay, and it's going to be very similar for Keras also, which you have handled before. It's so actually let me yeah, it's basically, I don't know if, yeah, I can't run this because I'm not imported the things before. So maybe I'll run it in a minute, but you can see that it's just going to be that sequential nature, right? So the diagram that we saw with some skip connections and all that, you can actually print it out and see how the model looks like. Okay, so this is how you instantiate the model. Okay. So once you get the model, for example, fine-tuning part, you just need to get rid of the last fully connected layer. So there's some ways to access the different layers. Okay, it's just .fc, for example, will give you the last layer, and you're just getting the input features, and then you're copying. What's happening in this example code is that we are picking up an ImageNet model. So the last layer is supposed to be a 1,000 class classification, right? We are saying, hey, what is the input dimension for the before I get to the 1,000 scores? Okay, let me take that number. Okay, that's input features. Okay, for the last thing, and I'm just going to take that number, and then I'm going to define a new last layer whose output dimension is 2, because it turns out that this example we just want a 2-class classification problem. So previously the fully connected layer would have had this number to be 1,000 because it needs to produce 1,000 scores. Now it's just 2. Okay, this is one way to change the last layer, and it's just changing the last layer, but you can change any set of layers if you want in a pre-trained architecture. So this is a way to instantiate that model. And dataset, I think some of you might have seen some handling of the dataset with the MNIST or fashion MNIST from before with TensorFlow. Here you will have somewhat similar ideas. Okay. Does that answer your question? I want to introduce one more thing, which is something new, but before that, I want to quickly check if these are built-in functions, basically. Yeah.
Yes, Professor.
Yeah.
Thanks.
So in fact, you'll be using many of the built-in functions, right? For example, what is the criteria? NN dot cross entropy loss, right? There are certainly some choices to be made. For example, here you can see optimizer. You need to say, hey, do I want to use SGD, or there are going to be some choices? Okay, ADAM optimizer or RMS prop, or so there's some different names. But at the end of the day, as I said, we know gradient descent. All these are some variations on gradient descent. Just figured out, folks have figured out what is the best way to get gradient descent working in the best way. SGD is literally the vanilla gradient descent. Vanilla is like the bare bones. And there's some learning rate and some momentum stuff that you can give as parameters. So these, I think you'll have to look at the documentation and say, hey, what would this extra feature do? For us, it doesn't, for us, it will be a black box, but you just need to know, hey, can I pass the learning rate that I saw in the lecture? Yeah, that much exploration you'll have to do. The second thing I wanted to quickly point out so that folks don't stop there is I think so many of you have already done this, which is to mount your Google Drive, right? So mount your drive so that if you want to read or dump information, you can dump information, you can read information, like if you want to read images, right? So in this example, actually, we need to get images from a URL, which is on the PyTorch tutorial website. And I downloaded it locally, and then I uploaded it back into Google Drive. You can do, there are many other ways, but this is one way I did it. I put it in drive /data. So you can, if I go back here, my drive data. So this is the data set that I unzipped here. And if you go into it, there's a train and validation folder. Within the folder, there are ants and bees. So it's actually an ants versus bees classification. So there's a bunch of ant figures and there's a bunch of bee images. Okay, so I've downloaded it, and then if you just want to mount it, you can mount that drive up to like you can see that here. When the last time I ran it, there were only collab notebooks and data. I think this time there's also a temp folder for some reason. But once you mount it, you can just read it. It's in the, once you are in the correct directory. So it says, hey, if you do an ls, you know that there is a collab notebooks directory and the data directory, and then you just have to say, hey, data slash, this particular data set is the data directory in this example. Okay, and of course, there's going to be some effort in trying to, because the data is arranged in a certain way, there are some I guess, there exists some pre-existing functions to read, for example, the names of the file names and things like that. Okay, and those, you'll have to look up the documentation, or we can talk about it next time. Okay, so for now, I didn't want to spend too much time here on that, except for that this is how you would load the data. Okay, and you can, as I said, this is literally opening the file that we saw on the GitHub thing. And one last point before I switch over from here is that this actually does both things. It does fine tuning of the ConvNet. It also does fixed feature extraction. So those are two things that we saw in the lecture just now, right? So have a look at the code base. This code base, it uses PyTorch, and see both the fine tuning example and fixed feature extraction example. Okay, we just saw, for example, where the model is. So there's some functions they wrote, and you have seen these types of training loops before. So, but it will be a good exercise, especially for folks who are new to Python, to play around with this notebook before jumping on to assignment 2. Okay? And because once you play around with this notebook, you'll be more confident with assignment 2. Okay. So here, I mean, fine tuning is what if we were just seeing that, hey, they just removed the last layer, made the output size to be 2, and it's a new linear layer. And once you have a new linear layer, its weights are randomly set, to be arbitrary values. And then you say, hey, let me now train it. Let me fine tune you definitely want to train the last layer, but you also can train everything else in the ResNet 18, other layers in the ResNet 18. Of course, you can choose some small learning rates for them if you want. So yeah. Any questions about this part?
Professor, can you please show us how to access other layers, just like how you have accessed the last
layer?
Yeah,
for that, yeah. I mean, you can literally print the, so this model object is just supposed to be, so for any object, by the way, let me run this. Running. So for any object, right, there are some nice quick handy functions that you can call to get a sense of what all is present in that object. So do we need this? I don't think we need all this. So let me go directly to the model part. Yeah, so because you're not doing all this stuff. Yeah, let me just copy paste here and press enter. Oh, it's actually for the first time. Yeah. So let me again go here. So model underscore FT. So you can actually, so this is an IDE, right? It's not the vanilla Jupyter notebook that you might be familiar with. So it actually shows you what all fields or functions are available. So there's in fact a huge list here. So that's for this object. So actually you can, if you just print it, right, it'll actually print out 100 different things. Okay, it says, hey, this is ResNet. Con1 is a certain type of a basic building block that they have. And then they have a bash norm, and they have relu, they have maxpool, and then they have and then they've defined layer 1 and so on. So you can actually, so maybe this is a little bit of a more complicated model, as you saw earlier. I was showing the ResNet 18 or ResNet 56 model. But if you if you do VGG, you will see a very simple way of like, and it's basically a dictionary. So I think dot. I don't know if it's a dictionary, so let me actually check in real time. So this is the handy thing I was saying. So if I do, if you did not have that IDE help, you can just do dir to get a sense of what all is present in this. So, I mean, of course, there's going to be a lot of functions that you are not supposed to see, like the underscore functions. But you'll see there are some, all these choices are there for this. So FP is what we accessed. Okay, and there's also access to layer 1, layer 2, layer 3, layer 4. So maybe they're just, keys, or maybe they're just variables which have, which maybe they're just objects which happen to be themselves dictionaries or some other objects and so on. So this, you can just try around to see what they are. For example, state dict is the one which will have the weights, if I recall. Yeah. So state dictionary will have will be a dictionary. So let's try model state dictionary, and let me dot keys. Maybe that was not a good idea. Oh, it's not a dictionary. Okay, this also you can try by just typing type. What is it? Oh, it's actually a function. Okay, so yeah, I think you should just try around and read the documentation to get a sense of like how the data is arranged. Okay.
Got it, Professor. Thank you.
Yeah, for fully connected and I think layer 1, layer 2, layer 3, I think there's some labels, but I would suggest the one, I think the basic thing that you want to try out with PyTorch, at least PyTorch based model or NN model based models that define, is how to get the weights out, how to put the weights in. Like in fact, there's functions like torch.load and torch.dump, which will let you dump a model to disk and so on. So you'll get a sense of, hey, where are the weights, how to access, how do I get to them, how do I enable the gradient computation, how do I disable the gradient computation. Those are things that you'll try out in this assignment too.
Okay.
So try out this example example notebook first, and then go to assignment 2 would be my recommendation.
Okay. Thank you.
Okay. I think that's all I wanted to say about the data loading part, that there's going to be some complication with respect to how the data is laid out. So this datasets object and data loader, datasets and data loaders are something that you will see maybe for the first time, some of you. If you have any questions on this part, for example, let's talk about it offline through any of the channels that we have set up. Okay. But I just wanted to show you that, hey, you can load data from Drive, which some of you might have already done for assignment 1. Okay, so now actually let's take a break for 10 minutes and resume at 7:40. And in the meantime, if you have questions, put it on the chat and we'll pick it up. Okay. Okay, so welcome back. I think there's a question about how do I know which layers are present in the model. So in PyTorch, actually, I kind of forgot about it. Is that you basically generally name your layers. And so in this ResNet 18, the layers are actually exactly the names that are given here. So it's con1, bn1, relu, max pool, and then so those are not the layers actually, sorry. Those are the names of these con, batch, and relu, and then they're being reused every time. Okay, so layer 1, layer 2, layer 3, and layer 4 are the 4, I guess, meta layers. Remember, there was this direct connection and a connection through like a bunch of bunch of layers, and so those are the 4, I guess, meta layers. And so you can see that the last one, for example, is just called FC. I mean, in a different model, it might be called something else. So you just need to, if it's not too big of a model, you can just print out. Whenever you print the model, it generally prints the all the I guess layers in that network, and so you can just get the names. Okay, layer 2 is, so if you do model underscore ft dot layer 2, you will basically get a handle on this meta layer. Okay, I'm just calling it a meta layer because it actually has a block. It has these several things. Con, bash norm, which we'll see right now, relu, con2, bash norm, and then downsample. All those things are there. Okay. So just a quick point on that. So let me resume with my annotation. Okay, so where are we now? So we have discussed up to this point. And what we'll do next is look at 4 related topics, in the sense that they're all basically extra things that you should know when you're dealing with a deep neural network, okay, and especially with a convolutional neural network, or especially working with images. One useful thing that folks generally do is called data augmentation, and these other things are, I would say, new transformations or new, I guess, parts of the model that were introduced to, introduced to improve regularization, improve prediction performance, improve the way gradients flow through the network, and so on. So remember, in every gradient update, gradients, there's a backprop step happening using the computational graph. So you can even, there are some tricks, in particular, batch normalization was one of the uh, ways in which you can ensure that gradients don't become all zeros or all become explode to really large values or things like that. Okay, so that's the next step that we're going to do. We're just going to look at 4 related but also unrelated, in a sense, 4 techniques. So let's start with the first one. Data and data augmentation. So data, I mean, we already know various ways to handle data. Tabular data, certainly we know we can make a SQL query, we can have CSV files, or even if it's if it's a really large data set, then maybe it's in a Spark cluster, or an appropriate data frame. Okay, so there are various considerations that go into working with data, but uh, especially with deep neural networks, they are data hungry. Okay, so if you don't do transfer learning, they only make sense when you have lots and lots of data. Okay, because we just saw the parameter count. There are just too many parameters to learn, and if you have very limited data, the model may not be able to figure out, like, it may just memorize the training data, for example, right? Which you don't want to do. So you want high quality data generally, right? And this is true for any modeling. And what we can do for image data specifically is a trick called data augmentation. And data augmentation is a very straightforward idea, okay? And it's quite popular, so it's worth knowing about it. So let's say you have this flow, right? So you have a data pair, xi, yi, ith example, right? An image and its label, and you pass it through some some convolutional neural network or something like that, and you get a loss value, and you use the data and the network to define the loss for this example, right? What you can do is, you have this data. For this data, I know what, for a given parameter, I can find the gradient of the loss with respect to the parameter. What I can do is create a new data pair, which is x tilde I, comma yi. Okay. So what I'm saying is, we can create for a given pair example xi yi. I can create another example x tilde I yi. Okay. And now I have 2 data points instead of 1. So I've really doubled my data set. Okay. And I can get a gradient of the loss with respect to this, with respect to parameters for this new example. Okay. So how did I get this new example from thin air, right? So this new example, x tilde I, so the feature part of this new example, or basically the image part of this example pair, x tilde I is just a transformation of the original image. Okay. And here is a quick example to demonstrate that. So what we're changing is basically the input image without touching the label. So the label is, is going to say, hey, this is a logo or this is not a logo. What it's going to change is the image. Remember, image is just a tensor. And so what we do is simple transformations of the image, where after that transformation, at least a human can know that, hey, it's still a logo or it's still not a logo, right? For example, let's say this is the original image. If you do, if you slightly change colors, if you flip the image, or if you do some cropping, or if you scale the image, on one axis and the other axis slightly differently, they all should hopefully be the images of a logo, right? So that's the key idea. And so it's not just doubling the data set. You can just increase the data set size by any multiple by trying out all these extra transformations for every original data pair that you have. And let's say you use all this data. So now you have this comma logo. I mean, logo or not logo, let's say the binary classification, this comma logo. And same thing. You have all these images and labels. You have now a larger set of data from which you train the CNN, okay, or some deep neural network. Now, what you can do at test time is get a test image. Okay, you get a test image, and you apply the same transformations. Okay, so you have the original test image. You apply this 5 or 10 different transformations. You get 5 or 10 different new test images. For each one of them, you try to make a prediction whether it's logo or not, and then maybe take an average. So that's the idea of how to leverage the idea that images, if there is some signal in the image, let's say the image should be a dog, even if you crop the image, let's say, the top border or the right side or something like that, hopefully the image still has the dog, dog specific features. And so you should still be able to say it's a dog. And so for example, in ResNet, which actually is the 2015 ImageNet winner, so what they do is scale images to these different scales, and at each scale they get so many different crops. So whatever is the original image, you scale it to 5 different levels. Okay, upscale, downscale, whatever is the original image size. Based on that, it's going to be upscale or downscale, and then create a specific size. Okay, and the specific size is exactly what I was mentioning earlier to John. And once you create the specific size, because maybe the CNN's input requires that size of the input tensor to have the right size of the output tensor and so on. You do these crops, and then you get so many images, and then you get a prediction for each one of them, and then figure out that's the majority prediction. So there's a question. So the question is, we see that part of the input lost in a few transformations. Exactly. Yeah. Does it not affect the model? Yes, it does. Yes. So it's not a foolproof method. So if you do crops, or if you do some transformations which completely mess up the meaning, right? So for example, there is like if it's an image of text, right, or a number, like, okay, and if you really do cropping of this text and say, so for example, let's say it's the image of let's say the number 8, okay, whether you do a flip, it really doesn't matter, right? But maybe if you crop it, it becomes a 3. Sorry, not this side, maybe the other side. It becomes a 3, and you're saying that in the training data it should be the label of a 8. Then yeah, you have a problem. So there are pros and cons of doing this. It's a good heuristic to deal with, having very little original data. If you think that there's some somewhat foolproof transformations that you can do on your original images and still say that, hey, the label is still should be the same. Okay. If you are not confident on that, yeah, certainly we should not do this. Yeah, as the name says, it's about data augmentation. So really augmenting your original data with extra data for free, especially for images. You can't really do that for tabular data, for example. I mean, you could, but there are certainly assumptions going on there, similar to assumptions here about spatial invariance. Great question. So yeah, I mean, other things that I did not show earlier is, change contrast, color, mix the translations, mix the translations, shifting patterns, rotation, stretching, many things that you can do. And in fact, in the example, in the example notebook that we just saw, I'm not going to change it, but let me see if there was actually some transformations going on at the top. Yeah, so I will not flip the source of screen share, but everybody who has the link to that, let me paste it in the chat anyway. So folks have linked to this. If you look at the cell number 3, okay, there is a transforms.compose, okay, some function which is getting a list of transformations. Okay, so you can see random resize crop, random horizontal flip. Those are the only 2 transformations being happening in this case. But if you look at transforms object in the PyTorch documentation, it'll say, hey, transforms with all these other things that we have been seeing in the lecture slide. So hopefully, if folks can click on that link and see cell number 3. So now let's come back to some other enhancements. The point is that there are several choices that we've already made, right? So for example, which activations to use, ReLU versus sigmoid versus Stanich versus, there's many other things, leaky ReLU that you've seen in your assignment. There are many choices, right? Cumulative number of layers, number of filters, and so on. But there are some other extra choices which turned out to be quite instrumental, at least in the previous few years, in really helping with training of deep neural networks. Okay, training for deep neural networks, by the way, is notoriously hard. And it's because gradients, it's a very complicated function, right? If the moment you keep composing with many different layers, you don't want to write a mathematical expression for it because there's a huge, lot of transformations going on with the input signal. And it's very hard to train, as in like get the best parameters, because it turns out that the loss function is not nice. In multi-class logistic regression, the loss function is somewhat nice, that it doesn't really matter where you start with, and you will get to a good linear model. That's what multi-class logistic regression will give you. But here there are a lot of challenges, and to address those challenges, there are a few things that folks have figured out: weight initialization, batch normalization, and dropout. A few of the things, and there are actually many more. Maybe when we talk about text, 2 lectures later, we'll look at a state-of-the-art text model called transformer architecture. And there you'll see a slight, instead of batch normalization, you'll see something called layer normalization. Okay. Some new, I guess, empirically validated enhancements to model that folks have figured out. These enhancements are hard to come up by yourself. I mean, I think it requires a lot of investigation. But once people discover these, and they seem to be general enough that they are suitable for many different, I guess, image-based image-based prediction problems, then it just becomes a part of the, I guess, model definition toolkit that you can use. So anyway, let's look at these three: weight initialization, batch norm, and dropout. So weight initialization is actually not much to say here, except for the fact that what I was alluding to earlier, that the loss function is going to be messy. So here's a one-dimensional cartoon depiction of how the loss function looks like, right? So if you do gradient descent, so if you had this one-dimensional loss function, if you do gradient descent, depending on which side of this hump you're on, this little peak, you will either get to global as in like the best thing that you could have done to the bottom of the valley, or to the left, which seems to be the best, the one with the lowest. Let's say the x-axis is, sorry, the y-axis is some sort of you want to minimize that, let's say. And instead, if you started on the right side of this little peak here, right side, then you get to a slightly different location, right? So, and this is just in one dimension. So you can imagine if you have a million parameters, right? So, or actually, just to throw a number out there, GPT-3, which is a model by OpenAI, which is a company the West Coast. So the GPT-3 model has 175 billion parameters, right? That's a lot. Okay, that's a lot of parameters, and you can imagine what the loss function. I mean, loss function in 175 billion space, you can't imagine. But even if you imagine, it's not a nice loss function where if you pick starting point for this 175 billion parameters, they get to some nice values. Okay, it's hard to navigate this optimization space. Okay, and that's where some folks have spent a little bit of time on trying to figure out what are some empirical heuristics that go well with many different problems. Okay. And we're not going to talk about those heuristics. If you're interested, just do search for weight initialization techniques, and you'll come across some, even the named initialization techniques. For example, initializing all the parameters to be from, let's say, Gaussian with mean 0 and some specific variance, is one named parameter, say named initialization technique. But we'll not be spending time there. But just we know that this is an important component of training a neural network, especially from scratch. Yeah, I mean, and the whole point is that these weights influence everything that happens next, right? So if your starting point is some W0 B0, you know that the gradient is getting computed with respect to them, and so the initial gradients depend on the initial starting point, and so on. So there are a lot of impact on the gradients themselves, and therefore the whole sequence of optimization steps that you'll take, a sequence of parameters that you'll visit till you hopefully get to maybe a bad minima or a good minima. Okay. So any questions about weight initialization before I talk about the next technique? Okay, so let's look at the next idea, which is called batch normalization. And again, this is not, so now people also use it as a layer, but the idea is some sort of introducing a nonlinearity or some sort of a change in the activation value. So think of this tensor view, right, or layered view we had. So every layer was producing something, a tensor or a vector. Think of fully connected feed-forward neural network. Then every layer is producing a vector, right? Activations, and those activations go to the next layer as inputs. Some linear transformation happens, and then nonlinearity happens, and then again you get a new set of activations. Let's stick with feed-forward neural networks. So what batch normalization does is somehow, come in between when you're going from one layer to another layer, so that the activations get transformed in such a way that it helps with training the neural network. Okay, so it's some sort of, you can think of some sort of transformation. So it's not exactly a full-fledged, fully connected layer or a common layer. Those were the, I guess, classical layers you would think of. This batch normalization just introduces an extra computation in between while passing between layers. Okay, and the motivation is activations, and their values. For example, remember ReLU's output is always 0 or positive. So if I have 10 neurons and all of them are ReLU, have ReLU nonlinearity following them, then my output is always positive, right? Maybe I want to recenter that activation vector. Recenter in the sense that maybe I want to make it between minus 10 and 10, let's say all the values, all the coordinates, right? So maybe that helps with subsequent computations that are going on in the neural network, right? So those are some of the motivations for which led to this idea. Okay, activation magnitudes and the statistics depend on not just the data set. They depend on definitely the network and the nonlinearity use, especially ReLU just pushes everything to the positive side, right? And these activations are certainly going to influence gradient propagation, because activation value, remember in the ReLU, if it's max of 0 comma whatever z, the local gradient is 1 on one side, and local gradient is 0 on the other side, right? So if there are a lot of activations which are not activations, sorry, yeah, if there are a lot of activations that are 0, that means that those neurons, really will not let gradients pass through. The neurons which gave to these activations values which are 0 will not let gradients pass through. So these are things that motivated folks to motivated folks to look for some ways to address these gradient propagation issues. And one of the outcomes from there was this idea of batch normalization. The idea is again, is a name, batch and normalize. Okay, there are two steps, right? So let's consider what is a batch. And once we know what a batch is, we'll say what normalization means. And normalization is something that, especially if you work with tabular data, you know what feature normalization or feature standardization means. Okay, if you have a feature, just take the mean value of the feature, subtract in every example or every row, subtract the mean value from the feature value, so that your feature is centered around 0, right? So you would do this, for example, as a pre-processing step before applying PCA, right? So so let's come back to batch normalization specifically. So what we do is the idea is to make each activation basically a standard normal. So something like 0, 1. Okay. So of course, activation is a vector, not a scalar. But if you think of it as if it is a scalar, then you just want it to be like if you take all these activation numbers and plot it, as a histogram, okay, then you should basically see a normal distribution. Okay, so so how do we do that? And we'll talk about how to normalize in a second. So yeah, so let's say we have the number of neurons as D, and we have a batch of n examples. Remember, we have, let's say we have 1,000 examples, and my batch size is 10. That means every time I'm doing this gradient descent operation, I'm only picking 10 examples to find the L data stuff that you remember from the first session or the second session, right? So batch size is those 10 examples that I'm currently doing a forward pass, and hopefully, I'll get a gradient with respect to parameters given only those 10 examples, right? So that's the batch size. Okay, what I'm going to do is, let's say at some layer, let's think of fully connected or feed-forward neural network. So fully connected layer, some hidden layer. Let's say the first hidden layer. Let's say the number of neurons is D. Okay, which means that for each example, okay, let's say there are 10 examples. Example 1 to example 10. Okay, so for this example, neuron 1 outputted something, neuron 2 outputted something, neuron 3 outputted something, 4 and 5 or whatever. Okay, whatever is the number of D. Okay. Similarly, you can view this as a matrix, because all this computation, remember, I am sending these 10 examples together in a batch essentially. So all of them are producing activations at the output of the first hidden layer. So those activation vectors, I just stack them one below the other. Okay, they're D in length because the number of neurons is D. Then what I do is I look at each column, which is like look at each neuron. Basically, each column is basically each neuron, each column, and then I just rescale. Okay, how do I rescale? I have let's say 10 numbers here, right? I have 10 examples of 10 numbers. I'll take the average of the 10 numbers. I'll take the standard deviation of these 10 numbers, and I'll subtract the average, divide by the square root of the standard deviation. Okay, for each of the input numbers. So let's say these 10 numbers. I mean, actually, let me do a smaller example. 5, 3, 1. Let's say for simplicity, let me just do it like this. Let's say there are 5 numbers. Okay, instead of let's say the batch is 5. Okay, take the average. Okay, the average is okay. Actually, maybe I should do 2. The average is 8 plus 8 plus 2, 18 by 2. Is this correct? Oh no, sorry, by 5. Sorry, I summed them up and then I'm dividing by the number of numbers. So the average is 3.6. Okay. Now what I do is from this vector, I'm going to get another vector, 5 numbers. Okay. So I'm just going to subtract 3.6 from each one of them. So I'll do here it's 1.4, it's minus 0.6, it's minus 1.6, minus 0.6, and 1.4. And then I'll multiply each one with 1 by square root of the variance of these numbers. Okay, so this is the output. Okay, that's exactly what's written here. This gamma and beta are just parameters. For now, in this example, I just said gamma is 1 and beta is 0, but you can add these extra parameters. Okay, and that's what the implementations in, for example, PyTorch or the implement, like for example, in ResNet, we saw that there was a bash norm block. They would generally have this parameter. So in that sense, it is a block which has tunable parameters. Things to tune are this gamma and this beta. Okay. So that's it. That's bash norm. So if you add this bash norm block, what's happening is from one, so everything is happening in batches, right? So the training is happening in batches. So whenever a batch comes in and you do a forward pass to get the gradient, you do the forward pass. While doing the forward pass from one layer to the another layer, if there's a bash norm block, then you get the output of the neurons, for each of the examples in the batch. For each neuron, you take an average and divide by, let's say, the variance, right? and then multiply with gamma and add some beta if there are parameters that exist. And then that's the new, so that's the new activation vector, activation prime, let's say, that's sent to the next fully connected layer. So for each, for each element in the batch, there will be a new activation vector. So what we did is take the old activation vectors and somehow transform it to new activation vectors, and they're just recentered in some sense. Okay. So that's batch norm, and it turns out that this function here is also differentiable. Remember, while doing gradient descent, we need the gradient of the final thing with respect to the initial, with respect to the parameters. So even if you put a batch norm as a part of a computational graph, turns out that gradients can still pass through. We're not going to do that computation at all. We're not even going to imagine the mechanical computation is needed there, but it turns out it is differentiable. Okay, so there is no issue with multiplying local gradients with the incoming gradients and all that stuff that we saw earlier. At test time, there's not going to be a batch. Okay, so what happens at test time is that the batch norm layer, and it's implemented the way it's implemented in PyTorch or TensorFlow, Keras, and all that, is that once the training is done, the batch norm layer not just only remembers if there are any parameters like gamma and beta, if they're there, it'll certainly learn them by gradient descent, but it'll also remember what is the expectation of that, or that neuron in the training data overall, and similarly it'll know the variance. So in the sense that it can still perform this step at test time if you just know this E of X and variance of X, and that you can remember when you're doing training. Okay, and the code bases are such that you don't have to touch anything here. It's just that they'll remember internally these extra numbers. Okay, if you want to, so that batch norm still works as intended in at test time when there's really no batching going on. Okay. So what happens? So if you had an original neural network without batch norms, original let's say CNN, all you do is introduce batch norm while going from one layer to another, and the question is, hey, why here? Why not somewhere else? That's again a design choice. Folks have figured out some right places to put batch norm. So con followed by batch norm followed by like a non-linearity followed by pool is what is in this example. But I think for ResNet we have that link, right? So maybe we can. Yeah, I don't want to switch the yeah, I don't want to switch the display immediately, but you can see like if you scroll a little bit down, you can see somewhere this batch norm mentioned. You can see con was followed by batch norm, is followed by relu, followed by con, followed by batch norm, right? So for us, it's just yet another block. All the computation is doing is exactly this. Any questions at this point about batch norm?
Professor, could you please explain again why batch norm is helpful?
Yeah, it was just something that folks discovered to try to influence gradient propagation. So remember, gradients may not propagate, especially relu always puts numbers on the positive side, right?
Okay.
So that's itself is, by the way, is not an issue. But the point is that relu can really mess up the gradient propagation in the sense that we know it does, right? For example, if the relu happens to be the input of the relu is negative, then we know the relu is not going to pass back the gradient at all, right? And similarly, on the positive side, it's a slope 1, so it's just pass back the gradient as is. So we know relu has certain tendencies. It turns out that if you just not use batch norm, it's very hard to control the gradients. Okay, either the gradients always become 0 when they go all the way to, let's say, the parameters of the first layer. So if you have the loss, they gradient with respect to the loss with respect to the first set of parameters, maybe in the first con layer, right? The first filters in the con layer will have parameters, right? If you want to compute the gradient, you do that local computation just in the computation graph. If you just imagine a computation graph, by the time you get to the parameters of the first layer, it may turn out to be zeros, okay? Zero gradients. So this is just one example of, I'm not saying that this is always happens, but the moment you make your models more and more complex by introducing and mixing layers and all that, there's a high chance of these things happening. And so batch norm is just saying, hey, let's correct the distribution of the activation vector. So the activation vector is basically a bunch of numbers, right? just recentering them so that each one is like basically between 0 and basically looks like a Gaussian, it's zero centered, and it's look like a Gaussian distribution if you plot a histogram. Yeah.
All right. And Professor, are there any inbuilt functions for batch now?
Yeah, it's everything is inbuilt. So actually all the layers are inbuilt. So con 2D linear layer we saw. I think some of you saw when you tried Keras, right? So in Keras you could chain together a bunch of layers. Batch norm is yet another layer.
Okay.
So
And
you just introduce them. Yeah.
Okay. And with respect to the gamma and beta, what would be the like most preferred values, or it depends on the model, right?
Yeah, great question, Supriya. So just for others as well, so this gamma and beta are tunable parameters of this layer you can think of. So remember, so you can actually tune them, not by trial and error, by your hand. You can actually train them so it'll learn the best gamma and beta while trying to minimize the loss function. So you'll have a gradient with respect to gamma, gradient with respect to beta as well. Every time there's a batch norm block.
Okay.
So if there are 100 batch norm blocks in the network, don't fret. Okay, like in the ResNet image that we saw that I've shared in the chat, there's so many batch norm blocks, right? They may all have different gammas and betas, but they all will be learned because they are also tunable. They are also parameters which will be updated, like gamma naught to gamma 1 to gamma 2 to gamma 3, so that the loss is minimized. Just like
we do not have to worry about updating or giving the values by ourselves.
No.
And is there a way that we can actually give, like, change the value of it if we want to?
Yeah.
Okay.
Any of the parameters that you see in the neural network, you can certainly hard code them to be fixed. Okay. And this is where I think you should try out the CNN code base that we have. This feature extraction business it has a similar idea, right? So in feature extraction, in transfer learning feature extraction part, you are saying, hey, all these parameters, there were some numbers that, because of training on ImageNet, I've already set those numbers. Now I don't want to change them, right? So what you can do is say that, hey, required grad is false or something. There's some way to say that, hey, for all these parameters, don't set the gradient computation to be true. Okay. The moment you do that, those are just they will not be changed. And you can also handpick a certain location, certain weight matrix, or certain bias, or whatever. For example, it's gamma and beta, and change them to be specific values. But people don't do it. But in feature extraction is a great example where if you don't want some parameters to change at all, you just say, hey, required grad is false for them.
Okay, got it. Thank you, Professor.
What's the time? 8:15. Okay. Yeah. So what we'll do is now look at one last, I guess, trick, which is dropout. I thought we'll get to an NLP today, but it's fine. We'll look at NLP next time as one coherent chunk. So let's look at dropout. So what is the motivation again? Again, the motivation is, hey, how do I improve my neural network performance out of, on the test? And is there anything else that I can do beyond regularizing the weights of the filter, or for the fully connected layer, the weights and so on? So is there anything more we can do? And the Turing Award winner, Jeff Hinton, and his colleagues figured out this idea called dropout. Okay. So what is the idea? It's a nice idea, which is as follows, right? So while doing training, what you do is you do a forward pass, right? So you have a batch of data, or you could have the full data. Typically it's batch. Okay, much of deep learning is you can't really use full data all the time. So in each gradient update. So you pick a batch. As you're passing the batch through the computation graph, remember, like, or even through the layers, getting a tensor, next tensor, next tensor, next tensor, and finally scores. If you have a batch, you'll have a bunch of scores for each example anyway. So as you pass through, do a forward pass. And in fact, in PyTorch, when you write your own model, the only function you need to specify is an initialization of what layers are there, and then a function called forward. Okay, and all it says is, hey, given an input, this is how I'll pass through all my layers, and this is my output. Okay, so when you do a forward pass, what you do is set the output of a bunch of neurons to 0. Let's say I have a 10,000 neurons in my whole network, okay, across all the layers. What I'll do is when I'm passing this batch through to get to the scores for each element, each example in this batch, I'll flip 10,000 coins, okay, of some probability, some bias, okay, let's say 50-50, maybe heads and tails. So I'll flip a coin 10,000 times, and for each outcome, I'll figure out whether this neuron's output should be 0 or not. Okay, if it's 0, then I'll explicitly force that the output should be 0 for that neuron, and if not, I'll leave the neuron as is. Okay, so what that effectively does is that if you had a neural network like this, okay, without dropout, and this is the figure that we've been seeing since a couple of sessions. Let's say it turned out that this neuron, this neuron, this neuron, this neuron, therefore, 2 of the neurons happen to land tails. The coin that I flipped happened to land tails, and 2 of the neurons landed head. So what I'm going to do is set the output to be 0. Setting output to 0 is the same thing as those neurons not existing at all, because whatever computation happened up to that point, whatever number, it doesn't matter. Right? It's gone. And if it's 0 as an input, 0 is not going to affect anything, right? So it's as if these neurons are gone. Okay, these 2, and so you have basically a reduced network, or some sort of like a network with some edges and some nodes missing. Or if you think of a computational graph, some edges and some nodes missing, basically. So you got some scores, okay? Scores. Ideally, you would have gotten some score 1, score 2. Here, you would have gotten some score 1, score 2, which are different. Right? Let's call it tildes. Some different scores, right? Because certainly the computation graph is different here. And similarly, if you do backdrop, you would have different gradient updates to the parameters here. Okay, so maybe W comma B here, some different gradient updates to these guys compared to the gradient update for this W comma B here. Okay, so that's it. That's the mechanism of dropout. Dropout just means every time I do a forward pass, let me drop off, let me kill some neurons basically in that computational graph. Okay? Let me remove them. Okay? And so that's so I'm telling you the procedure first, and then try introducing the motivation. So what is the point of dropout, right? The point of dropout is to do some sort of a regularization. So bring in some redundancy into the model. So what is it doing? If I drop off some neurons, and if I still have to classify a cat or a dog, if something looks like a cat, I drop off some neurons, I still want to classify it as a cat, then by doing dropout, I'm saying, hey, use lesser capacity, use some sort of redundancy, right? Even if some neurons are gone, you should still be able to tell me that this is an image of a cat or image of a dog. Okay? So it's forcing the model to use a smaller, it's forcing the model to use lesser capacity than what the model could have done without dropout, right? So in some sense, it's regularizing, constraining the model from being too, bigly in the sense, or too, it can, because the model can, without dropout, can fit something. With extra dropout, it's kind of forced to do, it's reducing its capacity, right? Because some neurons are anyway gone, some expressivity is lost, right? So in that sense, you can think of it as a regularization. And basically, we're building in some redundancy, robustness, or those are all informal terms that you can use here. So so basically, we are building in redundancy. So all neurons. So even if some neurons go off, we still have to predict correctly. That's what's going on here.
Professor, doesn't it mean like, okay, you're just cutting one part of the brain and then you're asking it to speak?
Yeah. If you, if you do a biological analogy, yeah, that's like that. But it's not deterministic, right? Here, it's pick arbitrary neurons and drop it. Yeah, every forward pass. So if you have, let's say, 1,000 examples, and if your batch size is 10, you will do about 100 forward passes, right? Let's say, like,
okay.
Right. So each time you forward pass, you flip, you drop something different. Okay, so that you build in this redundancy.
So are these the techniques which has been, built by people randomly or by just experimenting? Okay, to see.
Yeah. So how they have discovered these ideas, batch normalization, dropout. Yeah, these are researchers who have spent a lot of time on training these really deep neural networks. Networks which have at least depth of 3 or 4 or 5, they are really hard to train. Okay. So people are trying to say, how do I regularize? How do I ensure that the gradients don't become all zeros or all going to infinity or something? So yeah, there's a lot of empirical work here.
Is there a like technique that, okay, this neuron should get into 0? It's random, right? As you mentioned.
Yeah, it's random. So that's the point of random. It's randomization here.
Okay.
In the sense that for conceptually, every neuron you flip a coin and see whether you should make the neuron output 0 or not.
Oh, got it. Thank you.
Every time, yeah. So basically, it's some sort of a sampling. It's like, yeah, it's basically some sort of subsampling. You're basically picking up a small part of this neural network. Like, hey, layer 2, there's only these hidden neurons. Layer 3, there's only these other neurons, and so on. Okay? Every time you do a forward pass. So yeah, so you can think of it as subsampling. Yeah, and so remember, to drop the neuron, I have to flip a coin. Okay, and the coin is just a binary coin. It's just two outcomes, right? Head or tails. Head means I retain it, or tails means I drop the neuron. The bias of the coin, which is with what probability it should be heads, or with what probability it should be tails. Let's say the probability of tails, if I keep on increasing, which means that with higher and higher chance, I'm gonna kill a neuron, right? A neuron, and I'm doing many for every neuron separately. Higher probability means basically stronger regularization, because I'm killing more neurons, okay, which means that I'm lesser and lesser expressivity of the model. Okay? We're constraining the expressivity of the model. Now, at test time, what do we do? So we have introduced dropout. We built this model. Does that have an impact at test time? Remember, if we had some impact on batch normalization, for example. There's no batch at test time. We have a single image, let's say. So at test time, there are a few things you can do. You can say, hey, there's no dropout. But if you don't drop out neurons, what happens is, because now all the neurons are present, the signal somehow gets amplified. It gets shifted, because typically you would drop, let's say on average you drop out 50 neurons, okay, and all the 50 neurons add up to some, let's say, the final score, let's say, then your output is some 10 units. But if you don't drop half the neurons, then maybe output becomes 20. Okay, so there's some scaling issue, and the way people fix it is, let's say the probability of dropping out is let's say probability p. Let's say it's 0.5 or something. Then originally, this is the original function. Let's say with the one hidden layer neural network, then this is something we've seen in assignment 1 as well as a couple of lectures ago. So W1, B1, W2, B2 is exactly this function. Now, if this is the original function and you introduce dropout on the hidden layer, so remember, it's exactly this picture that we've seen, right? Introduce the dropout in the one hidden at the hidden layer. Then what you do is at test time, you retain all the neurons, and so because I retained all neurons, the output, as I said, could get shifted. Okay, if there are only 25 neurons feeding to the score, now it's 50 neurons feeding to the score, then you can reasonably expect that maybe my score is probably double than what at training time I was looking at, I was seeing, right? So you can just multiply with p. That will just divide by half, right? So this is something that for us, it's just for us to know that what's the change from at test time, but this is some extra thing that folks do. And this, by the way, there's a dropout. Again, you don't have to code it from scratch. Dropout is something that you can invoke in PyTorch as well as Keras by just calling dropout. Dropout as a step in your definition of your model. And I don't recall it at the top of my head, but maybe this step is also taken care of. Okay, you don't have to do anything actually while doing testing. It's taken care of, just like in batch normalization, it's taken care of when you send a test image and try to get a prediction of cat versus dog. Similarly, when you set the test image here, PyTorch, for example, PyTorch's dropout implementation already takes care of this. Okay, so that's dropout. At this point, we are closing up on CNNs, and next time we're going to switch gears and talk about text. Okay, so we are going to pause on images for now, talk about text, and again we're going to come back to images intermittently, as well as when we talk about generating faces and so on, when we talk about GANs. Okay. So anyway, so any questions about dropout?
You mentioned that the dropouts happen in hidden layer, and it is not going to happen in the input layer, right?
No, dropout is done on any neuron. So input layer. I mean, if you think of input as a layer, then yeah, it's not backed by a neuron, right? So these guys, this is not really backed by a neuron. You could certainly drop. What is it?
Could you please repeat it? I didn't.
All I'm saying is, think of dropout as just a, for every neuron, there's somebody sitting on top of the neuron and flipping a coin. Input layer I mean, input layer is just a bunch of numbers, right? I mean, you can certainly drop those numbers also if you want, but that's really not considered dropout, I think. But yeah, just think of dropout as at every neuron, somebody sitting there and flipping a coin and making the neuron inactive, basically. It's not part of the computational graph. If you think of a huge computational graph, yeah, this is just turning off some part of the computational graph.
Okay, it can be any neuron, as an input, hidden, output, any.
I mean, input is not really a neuron, right? So remember this function we have seen here.
Okay.
The function. So the dropout only what it does is affects instead of wx, w transpose x, there'll be a 0 there. That's all.
Okay.
And here, in fact, in that picture, there's only going to be dropout at the hidden layer, because you may not want to drop out at score level, because if you drop out the score, then the score will be 0 or something. Yeah.
Got it, Professor. Thank you.
Yeah. But good question. So dropout is just happening at neurons. Now you can certainly have dropouts at some layer and not have dropout at some other layer. So so you can do dropout at, let's say, layer 1. It happens to be con layer, and maybe layer 10, which is right next to the scores output. You may not drop out. Okay, so that also you can. There's a flexibility. Yeah.
Got it.
Yeah. So as you see the example notebook, so I'm keep referring to that notebook. So that notebook has bash norm and what I think. Oh, it doesn't have dropout. Bash norm.
Professor, I have one.
Because okay, it doesn't have it explicitly, because if once you print out the ResNet model, you'll see some details. Yeah. So sorry, it doesn't have dropout, and I think there's a different notebook, I believe, in the examples folder, which has dropout on bash norm example.
Okay. I have one more question. I guess you did explain the last sentence in the previous previous slide. Could you please explain that? Thus, we get an ensemble.
Okay. So this is actually just interpreting. So remember, so this is first interpretation. What is dropout doing? It's just regularizing, in the sense of reducing the capacity of my network. Okay, so reducing the capacity of my model.
Yeah.
Now, the second interpretation is that every time I do a forward pass, I have basically a different model, like model 1. Second time I do a forward pass, there's some other neurons, therefore it's a slightly different model. Similarly, 10th time or 100th time I do, I have a slightly different model. Yeah. So you can think of, these are all individual components of an ensemble. Okay. And at test time, when I don't drop out, okay, it's as if all these models are fading in. Okay. It's like an ensemble average that's going on.
Okay.
It's just it can be made more precise, but I didn't want to spend too much time there. But yeah, I just think of that each one is a neural network. Okay. After dropped out, each one is like an example neural network. If you combine them, at test time, I'm not doing dropout, right? So either I scale things and so on, but that's fine. It's as if I'm averaging out a bunch of individual models. That's all. That's what ensemble means. And of course, they all share parameters, because they're all, they have common neurons, right?
Okay, got it. Yes, Professor.
Actually, we are going over time, so thank you, everyone. And if folks still have questions, do stay on, and we can discuss. Even if you have basic questions, certainly stay on and ask. It's good to clarify when you have the context and so on. Yeah, thanks. I'll stop the recording now before